This video discusses data storage on Biowulf and the NIH HPC systems. The first thing to know about storing data on the NIH HPC systems is that users are prohibited from storing personally identifiable information and personal health information on any of the storage that the HPC systems provide. PII and PHI are defined by NIH policy, which users should be familiar with from the annual security and privacy training. Controlled access data, for example, data from dbGaP or the UK Biobank, is permitted to be stored on the HPC system storage. However, you, the user, are responsible for fulfilling all of the requirements set out by the data provider to ensure the security of that data. And if you have any questions about how to do that, you should consult the HPC systems documentation on access permissions to data and email staff@hpc.nih.gov with any questions. So, once you have your account on the NIH HPC systems, there are several places where you can store data. The location where by default data is usually stored, for example, when you first log in and create a file, is your home directory, which is /home/your username. It is a network file system that is created with your HPC account, and it is notably the only storage system that by default is backed up to tape. However, you do not have very much space in your home directory. The quota is 16 gigabytes, and that cannot be increased. It is available from Biowulf, Helix, and the compute nodes. The place where you will probably store most of your research data is the data directory, which is /data/your username. And that is also a network file system that is created by default when you get an HPC account. There are snapshots that can be used to recover accidentally deleted files, and we'll discuss how to do that later. And the default quota is 100 gigabytes. However, you can request an increase in your data directory quota, unlike your home directory quota, which is fixed at 16 gigabytes. There are also the notion of shared data directories for if you are in a group of collaborators, for example, all of the members of a lab. We will discuss those further later in this video. Another location where you can put data, albeit only temporarily, is Scratch. We recommend that you create your own directory within /Scratch to store your data if you wish to use this. So for example, you can create a directory /Scratch/your username, and this is something that you can do yourself. It's a low-performing shared file system. It actually has 75 terabytes of space that's shared by everyone. However, that space is in the process of being increased. Please check the HPC system documentation, which will be referenced later, to see the current size of Scratch. And as of this video being produced, each user can only store a maximum of 10 terabytes in Scratch if it's available. And also there is LScratch, which is created by a batch job running on the cluster. Usage of LScratch, which is local disk space on a compute node, will be discussed in a later video. Let's talk a little bit more about Scratch. As mentioned, it's a large but low performance area that is shared by all users on the system. As a result, it can often get bogged down and become very slow to access data in Scratch. As I mentioned, there is a 10 terabyte maximum amount of data that can be stored per user. However, we do not guarantee that 10 terabytes will be available at any given time. In addition, Scratch is meant for temporary storage, and files will be deleted 10 days after they are last accessed. And writing programs or scripts to automatically update the access time of files via the touch command is prohibited. And if the HPC staff catches you doing that, your access to Scratch will be locked. You will not be able to use Scratch anymore. Files, as I mentioned, are deleted 10 days after last access, but if Scratch starts to get full, the HPC staff will delete large files as needed. Don't use Scratch as temporary space for a large number or a group of jobs. That is to say, do not have 50 or 100 jobs all writing to Scratch. Since it is a low-performing space, that will overwhelm the file system. You should, instead of using Scratch, use local disk on nodes, which is lscratch, as temporary storage of transient job data whenever it's possible to do so. Let's talk a little bit more about data directories. Most data directories are on high-performance parallel file systems that use a file system called GPFS. The HPC staff currently maintains 25 petabytes of GPFS space. It's important to note that sometimes in the output of various commands that you might run on the cluster, your data directory might be referenced as another name. For example, instead of /data/ your username, you might see a path like /GS11/users/ your username. This is because the /data directory actually contains links to different locations where the data is actually stored. However, because the storage administrators can and often do move data directories between different file systems, you should always use /data/ your username, or in the case of a shared directory, /data/ whatever the name of the shared directory is, instead of the /gs whatever or /spin1 path, because that way, if your data directory is moved, your scripts will continue to work. You can check quota and usage using the check quota command, which will show output similar to that shown here. We can see here that for this particular user, their data directory has a quota of 500 gigabytes, of which 125.8 gigabytes have been used. Their home directory has a quota of 8 gigabytes. This was done back before we increased home directory quotas from 8 gigabytes to 16 gigabytes, of which 2.4 gigabytes have been used. Please note that the data directory also has a limit on the number of files that can be stored on it, slightly over 31 million. All storage systems have limits on the number of files that they can safely store, and therefore the HPC staff places limits on the number of files that may exist in any particular data directory or its subdirectories. In general, these limits should not be high enough to cause any problems. However, if you are getting close to your number of file limit, you probably need to discuss your workload with an HPC staff member, since increasing the limit on the number of files is not something that we can generally do. So if you find yourself getting close to the limit on number of files, you should really have a talk with us about how you're storing data, what kind of files you're storing, and why there are so many of them in your data directories, and we can make some suggestions on how to lower your file usage. So, as I mentioned, there are quota increases available for data directories, i.e. you can request more disk space. You generally, as I mentioned in the previous slide, cannot request an increase on the maximum number of files you can store, but you can request an increase in the amount of available space. And you can do that through your user dashboard, which is accessible from within the NIH network or VPN at the URL shown on the slide. Once you've logged in, you can click on the Disk Usage tab, and you'll see all of the file systems that you have access to. And you can see that you can, for those that you're allowed to request a quota increase for, there's a button that says Request Quota Increase. And if you click that button, it will take you to a form that you can fill out. One thing that we do ask is that instead of running to the quota request form, please think a little bit about whether you can be using space more efficiently. For example, if you have data that you're not actively processing on the system, you can move it back to your local computing and storage infrastructure, if possible, if your IC provides storage space for you. You can delete any raw data or intermediate files that you're sure you won't need again or that you have already backed up elsewhere. Also, for data that perhaps you don't need to access right away, you can compress the files using gzip or bzip2 when they're not in active use. There are some types of data files that should always be compressed. For example, FASTQ files, which contain raw sequencing data, should always be compressed. In fact, many genomic software packages can deal natively with gzipped FASTQ files, so you don't even have to uncompress them to use them. Likewise, SAM files should always be converted to BAM files for genomics users, because that BAM is a compressed binary form versus SAM, which is a uncompressed plain text form. Not all files will compress well. For example, molecular dynamics binary trajectory files generally do not compress well at all. So you have to know a little bit about the compressibility of your data. Storage space on the NIH HPC systems is never to be used for archival data. That is to say, you should not ever just store files on the system that you're just storing in the off chance you should need them again. Data storage on the HPC system is intended to be used for files that you are at least somewhat actively computing against or may do so in the near future. As I mentioned, it's possible to create shared data directories. That is, a data directory that is shared amongst multiple users. These users will be created in a special group that has the same name as the shared data directory, so they can all access the data directory. It's important to note that if you request a shared data directory, which you can do under the storage menu, you will become the owner of that shared data directory, and you are the only person that the HPC staff will accept quota increase requests or changes to group membership from. That is to say, no one else in the group can request a quota increase or can request to add or remove other users from the group. Only the group owner, that is to say, the person who requested the creation of the directory, can do that. Another common issue with shared directories is managing permissions in them. On the HPC systems, members of a shared directory are responsible for ensuring appropriate permissions are set on files and directories within the shared data directory such that all members of the group have the access that they need. Let's talk about snapshots. The home and data directories have snapshots associated with them. The home directories have 6 hourly snapshots, 6 nightly snapshots, and 8 weekly snapshots. Data directories have 2 daily and 2 weekly snapshots. What a snapshot is, as the name implies, a view of the directory as it was at a particular point in time. For example, if a nightly snapshot is created at 1 a.m., the contents of the snapshot will be exactly what was in the directory at 1 a.m. on that morning when the snapshot was created. Snapshots are useful in case you accidentally delete a file or overwrite a file in the directory. You can go back into one of the prior snapshots, and if the file is present, you can recover the original contents out of the snapshot, and I will show an example of this. However, snapshots are not backups. They do not protect against a catastrophic failure of the storage system. Consequently, if you have any data that you absolutely cannot afford to lose, it is your responsibility to back it up. Snapshots are not backups. So, we will do a brief demo of snapshots. So, let's look at snapshots in practice. Here I am in my home directory, and let's suppose I accidentally delete something. For example, the subdirectory called NAMD. I'm going to accidentally delete it. Now, suppose I realize after I type the command to remove the directory that I actually needed that directory. Oops, it's not there anymore. However, snapshots can save me. I can go into my .snapshot directory. Note, you will not see it when you list your directory. You have to change into it explicitly, and we'll see the snapshots that are available to me. So let's pick the latest hourly snapshot, which would be one taken at 8 p.m. on the evening this video was made. And let's look, and we can see the directory that I accidentally deleted is still there. So I can copy it back to my home directory. That'll take a second. And if I go back to my home directory and I look, the directory is there. And disaster has been averted. So snapshots can be used to restore files or directories that are mistakenly deleted or that were mistakenly overwritten with other contents. That's precisely what this slide is showing. You can Once you're in your home directory, if you do an ls-a, you will not see your .snapshot directory, but you can change to it. You can change into any of the snapshots, and you can copy files back into your main directory. There are a number of best practices for storage. You should not submit large groups of jobs without knowing how much data they will generate. However, you should submit a single job, figure out how much data it will generate, and extrapolate out, and then make sure you have enough space left in your output directory to store it. Again, you can use check quota to check the amount of space you're using versus the amount of space you have available under your quota. Also, you should not create directories with more than 5,000 files in them. As I mentioned, there is a limit on the number of files any storage system can hold. However, there are also some limits on the number of files that can exist in a single directory. Nothing will break necessarily if you create directories with more than 5,000 files. However, they will be very slow to access. If you type an ls, it will take a long time for that ls to return. If you try to do anything like move a file in or out of that directory, it will take substantially smaller. You should not have, if you're working as part of a collaboration, you should not have each member of that collaboration have their own copy of data files unless they're going to be working independently on that data and are going to need to modify their own copies. Instead, you should ask for a shared area and keep shared files there to minimize duplication of data. The HPC systems have a large amount of space, but even petabytes and petabytes will not last forever if used unwisely, and there are lots of duplication of large data sets. Do not, as I mentioned, use Biowulf storage for archiving. Move unused or old data back to your local system. Likewise, be careful about your file access patterns. If you have 100 jobs all reading a copy of the same file out of your data or home directory, you will very quickly saturate the shared network file system. You should use local disk on nodes, and you should copy files there and have each job access the file on local disk. And it's important to note, if the jobs are only going to access the file once, well, your copy accesses the file once, and therefore there's no real advantage to copying to local scratch. But if the jobs all read the same file over and over, then you definitely will find it advantageous to use local scratch, and you will be less likely to saturate the file system. If you do saturate the file system, chances are you will hear from the HPC staff, and we will advise you on ways you can refactor your workflow to avoid that in the future. Likewise, do not use any of the shared file systems to write and delete large number of small temporary files. For example, temporary application files. These should be done on local disk. You can find more information about using storage on the NIH HPC systems on our website, specifically hpc.nih.gov/storage. And as always, if you have any questions, you can email staff@hpc.nih.gov.